Okay, let's talk about vectors in 3 dimensions. We'll be doing all of the learning objectives in this particular section. So we want to now move from 2-dimensional space to 3-dimensional space by adding a z-coordinate. We want to be able to move around in 3-dimensional space. We're going to talk about the distance formula in 3 dimensions, which is a very straightforward extension of the 2-dimensional distance formula. We'll write equations for simple planes and spheres. We'll do more complicated planes later, and we'll talk about how the vector operations that we learned in the previous section generalize to 3 dimensions. And this notation right here, this capital R with the superscript 3, that's how we will symbolically represent 3-dimensional space. So we take a 3-dimensional space, we take 2-dimensional space, and we make it 3-dimensional by adding a z-axis. Traditionally, we have the x-axis and the y-axis in 2 dimensions, and traditionally the third dimension is represented by the z-axis. There is some ambiguity on how to add that third dimension. Which way do we point the z-axis? And there's actually a rule for that called the right-hand rule.
So the idea here is that we're going to take vectors that were living in the plane, 2-dimensional vectors, and we want to lift them up into three dimensions. So not only do they have sort of a position in the xy plane, but now they have a position vertically. And in this way, we can kind of identify every point in 3-dimensional space, which is clearly useful to us as we go on and do applications in Calc 3. We do have a quick technical detail that we have to deal with, and that is some kind of convention on orientation. When we're plotting or when we're creating coordinate systems, we typically create a 2-dimensional coordinate system with a big old horizontal x-axis and vertical y-axis. Of course, to create a 3-dimensional space, we need to add another direction. And we could make this new direction coming out of the plane or going into the plane. Out means that this is the positive direction, and in means that down or into the table is the positive direction. How do we eliminate this ambiguity? How do we make sure that mathematicians and physicists and other scientists all over the world are working with the same orientation? Because it actually is going to matter later whether we make this the positive direction or this the positive direction. And the answer is something that the whole world has agreed on, something called the right-hand rule. And the way that it works is you orient your fingers on your right hand in the direction of the positive x-axis. You put your thumb up, and then you have your palm towards the y-axis like this, and this tells me which way to point the positive z-axis. So once again, you line your fingers towards the positive x-axis, your palm is towards the positive y-axis, and your thumb on your right hand naturally points in the proper orientation. If I were to make a different choice for my xy plane, let's say that this is the positive x direction and this is the positive y direction. I put my fingers along the positive x-axis and my palm towards the positive y-axis, and my thumb is pointing down. So the correct right-hand orientation for this 3-dimensional coordinate system would be to have the z-axis being positive down into the table. So for this plane, we point our fingers towards the positive x-axis, our palm towards the positive y-axis, and our thumb points in the positive z direction. That tells us how to orient. And here we put our fingers in the direction of the positive x-axis, our palm in the direction of the positive y-axis, and our thumb tells us which way the positive z-axis should go, and that's the right-hand rule.
In two-dimensional space, there was only one plane, the coordinate plane. In three-dimensional space, there are a multitude of possible planes that can exist in three-dimensional space. Planes are sort of two-dimensional objects that sit inside of three-dimensional space. And for example, three very special planes are the xy plane, the yz plane, and the xz plane. The xy plane is the collection of points whose z-coordinates are 0. Similarly, the yz plane is the collection of points whose x-coordinates are 0, and the xz plane is the collection of points in all of 3D space whose y-coordinates are 0. It's really important to think about collections of points or sets of points in three-dimensional space. So keep that idea in your head as we go forward. The three-dimensional space is divided up into octants, just like we had quadrants in two-dimensional space, the first, second, third, and fourth quadrants, and we all kind of know where they are. There are octants in three-dimensional space, and they're defined as follows. Frankly, it's mostly just important to know that there are these 8 sort of partitions of three-dimensional space. Mostly the only octant people typically talk about is the first octant where all 3 coordinates are positive. The other octants kind of go in the way you might expect. So this is the first quadrant in the xy plane. Above it is the first octant. This is the second quadrant in the xy plane. Above it is the second octant, and so forth. So we go first, second, third, fourth octant, fifth, sixth, seventh, eighth octants down below. Once again, I wouldn't worry too much about, for example, the fifth, sixth, seventh, and eighth octants. Nobody really knows which ones those are unless they're really thinking about it. It's not something that comes up naturally. You may remember that the distance formula in 2 dimensions is just the difference of the x-coordinate squared plus the difference of the y-coordinate squared, all square rooted. Amazingly, the distance formula in 3 dimensions generalizes in exactly the way you might hope. You have the 2-dimensional distance formula that kind of stops here. You want 3 dimensions, just add another difference of coordinates squared and take the square root. Why does this work? You can kind of best imagine this. Let's say we're trying to compute the distance of this diagonal part of this box. Project that diagonal down into the xy plane. You can figure out this length, d1, by the traditional 2-dimensional distance formula. That is x1 minus x2 squared plus y1 minus y2 squared, all square root. Once you have that, you can figure out this distance by another application of the Pythagorean theorem, because this is a right triangle. The thing in the orange is a right triangle. So you get d1 squared plus z2 minus z1 squared, all square root. And when you write it all out, you just end up with this. Interestingly, this generalizes into higher dimensions, 4, 5, 6, n dimensions. Very handy formula, and pretty convenient that it generalizes in such a natural way. Okay, 3-dimensional space is geometrically very different. For example, in 2 dimensions, 2 lines are either parallel or they cross, they intersect. In 3 dimensions, you can have parallel lines, meaning they point in the same direction, or you could have intersecting lines, but you can also have 2 lines that are not parallel and that don't intersect, and that's a thing that can't really happen in 2 dimensions. So with all this extra room in 3 dimensions, we have some perhaps counterintuitive geometric possibilities. Similarly, you can have 2 circles that kind of overlap but don't intersect. These are interlocking circles. Equations generally and in 3 dimensions are really important ideas, and I don't know what your intuition about equations has been in the past, but in this class I want us to be thinking about equations as defining sets of points. In other words, an equation is a membership test for a collection of points. Um, when you're talking about equations, the dimension matters, the context of the equation matters. When I write the equation x equals 0, in one dimension, it's a point. It's all of the points in the number line for which x is equal to 0. Well, there's only one point in the number line for which x is equal to 0. But if my context is 2 dimensions, then I'm asking the question, well, what does the set of points look like where the x-coordinate is 0? Well, all of the points along the y-axis satisfy that condition. Every point along the y-axis has its x-coordinate as 0. So it's a completely different situation. In 2 dimensions, I get a line. In 1 dimension, I get a point. In 3 dimensions, the situation changes again. Now I'm asking the question of all the points in 3-dimensional space, x, y, z, what does the collection of points that have their x-coordinates 0 look like? And that's actually a plane, and it's the yz plane. It's the plane that contains the y-axis and the z-axis, and the x-axis is kind of perpendicular to it. So the context matters. If I say, what does the collection of points that satisfy the equation x equals 0 look like? You have to come back at me and say, well, what do you mean? Do you mean in 1 dimension, 2 dimensions, 3 dimensions, 4 dimensions, 7 dimensions? What are you talking about? So equations are, in a sense, membership tests. And if you satisfy the equation, then you're part of this set. If you don't satisfy the equation, you're not part of this set. The equations of the planes parallel to the coordinate planes look like this. For example, z equals c is an equation. The collection of points whose z-coordinate is c is essentially a horizontal plane sitting at position z equals c. Similarly, y equals b, this is going to be a vertical plane. This vertical plane is the collection of points whose y-coordinates are b, and they are going to be and that plane is going to be parallel to the xz plane. All right, let's do a quick check here. Write an equation of the plane passing through the point 1, -6, -4 that is parallel to the xy plane. Well, if you're parallel to the xy plane, you're kind of like this. And to pass through this point, it means you have to be at the right position to capture -4. So the way to do that is write z equals -4. Okay, so that's going to contain this point. Another simple but useful collection of points that we like to consider in this class is the sphere. The sphere geometrically is the collection of all points that are the same distance r from a fixed point, the center, ABC. Now that we have the three-dimensional distance formula, we can very quickly write an equation that describes all of these points. And that equation is this. So we have x minus a squared equals plus y minus b squared plus z minus c squared equals r squared. This comes directly from the distance formula. The only difference is there's no square root. We've squared both sides. So what we're saying is the distance from x, y, z to a, b, c is equal to r, and it makes no difference whether we square that or not. So we square that equation just to get rid of the square root, and we get the standard equation of a sphere. ABC is the center, r is the radius. We could find the standard equation of the sphere with center 10, 7, 4 and point, the standard equation of the sphere with center 10, 7, 4. I think this should say containing the point, -1, 3, -2. In order to do that, we have ABC here, so that's no problem. We need to figure out r in order to satisfy this sort of standard form of the equation. How are we going to figure out r? We're going to compute the distance from this point to this point using the distance formula and drop that in for r. There are lots of different ways to kind of ask the same question. For example, suppose we have 2 points and we have a line segment PQ that goes between those 2 points. What's the equation of the sphere if PQ is the diameter? Well, if PQ is the diameter, then the center of the sphere sits at the midpoint of this line. So we have to find the midpoint of the line segment connecting PQ. That's just the average of these 2 points. And the average of 2 points in 3 dimensions is just coordinate-wise addition divided by 2. So for example, -5 plus 3 is -2, divided by 2, -1. So the x-coordinate of the midpoint of the segment PQ is -1. You go across the coordinates, you compute the coordinates of the midpoint, and then you use those along with half the length of this line segment, so you're going to have to use the distance formula, and use those in the standard equation of the sphere. At this stage of the game, we can't really graph too many other kinds of equations in 3 dimensions, but we can do a couple of things. For example, this equation, x minus 4 times quantity z minus 2 equals 0, is a set of points that we can graph. X minus 4 is the collection of points whose x-coordinates are 4. Z minus 2 is the collection of points whose z-coordinates are 2. If this equation is to be satisfied, one or both of those conditions must be satisfied. So this is kind of an or. So we look at the collection of points that satisfy x minus 4 equals 0. That's a plane that's parallel to the yz plane, passing through the point x equals 4. On the other hand, this is a plane that's parallel to the xy plane, whose z coordinates are all 2. So in combination, this is the union of those 2 sets. So the set of points that satisfy this equation is the plane x equals 4 and all those points, union with the plane z equals 2, all those points. Other equations in 3 dimensions, at the moment we can do circles, we can do planes, very simple planes, not much else. We'll talk about those other kinds of things later. Thankfully, vectors in 3 dimensions generalize by simply adding a z-coordinate to the standard form. So in 2 dimensions we stopped here at xy, in 3 dimensions we add a z-coordinate. Those vectors live in 3-dimensional space and can be plotted accordingly. You go out in this example, you go out 2 units along the x-axis, 4 units along the y-axis, and 1 unit up in the z-axis. All of the operations work just the same. Vector addition is component-wise, scalar multiplication is component-wise, and all of the same kind of geometric ideas hold. The standard unit normal vectors, I, j, and k, look like this. K is the new one for the 3rd dimension, and it is just 0, 0, 1. We also have displacement vectors, PQ. So if you want the displacement from P to Q, you just subtract the 2 points. Q minus P gives you PQ. Geometrically, vector addition kind of works the same way. We have a vector here A and a vector here B. The sum is just the vector that lies in the plane containing these 2 vectors. And it's just the diagonal of that parallelogram as we discussed in the previous section. Here's a summary of sort of property of things that we can do with vectors. If we have 2 vectors v and w in 3-dimensional space, we have scalar multiplication, vector addition, vector subtraction. We have the magnitude of the vector, which is just the sum of the squares of the coordinates square rooted, and we can form unit vectors in 3 dimension by dividing the vector by its length. Okay, let's do a quick set of examples. First example, let's go and check our notes here. Let's talk about problem 64. So in problem 64, you're asked to describe and graph the set of points to satisfy the given equation. So here we've got z minus 2 times z minus 5 equals 0. So we have a z minus 2 times z minus 5 equals 0. And as we've already kind of mentioned in the earlier example, this means either z is equal to 2 or z is equal to 5. The plane that corresponds to so if I put positive x here, positive y here, then by the right-hand rule, positive z is going up. At z equals 2 units up here, we've got a plane that looks like this that kind of strikes right here, and then another 3 units up. I guess I should be a little more careful here. This is 1, 2, 3, 4, 5, and then we've got another plane up here that kind of runs in parallel. Really hard to sketch these things, but hopefully you get the idea. We've got 2 parallel planes, z equals 5 right here, and z equals 2 right here. And the set of points that satisfies this equation is the union of these 2 sets of points, the union of all the points in the top plane and the points in the bottom plane as sets. Let's move on to 68 here. In 68, we want to write the equation of the plane passing through the point 1, negative 3, 2 that is parallel to the xz plane. So things that are parallel to the xz plane are planes with constant y. What's the y-coordinate of this point? It's negative 3, and so the equation of the plane is simply y equals negative 3. Problem 70. Find an equation of the plane passing through the points 1, 9, 2, 1, 3, 6, and 1, negative 7, 8. Passing through the points in our set kind of idea, one could change that language to containing the points. In other words, these points pass the membership test of whatever this equation is. If you look at these points, you notice that in each case the x-coordinate is 1. So if we chose the plane x equals 1, we would have the equation of the plane that contains these 3 points because they all pass that membership test. What kind of plane is that? That's a plane that goes through the value x equals 1 on the x-axis and is parallel to the yz plane. Okay, let's look at 76. In 76, we want to find the center and the radius of the sphere with the given equation. I chose this one because it illustrates a technique that you should all sort of refamiliarize yourselves with. Let me make a copy of this. So if we're going to identify the center and the radius, what we really need to do is put this into standard form, and that means getting it into the form x minus a squared plus y minus b squared plus z minus c squared equals r squared. How are we going to do that? We're going to group the x terms together, the y terms together, and the z terms together, and then complete the square. So if we take x squared minus 6x and we complete the square, we get something like x minus half of negative 6 is negative 3. We square that. By introducing this representation, x squared minus 6x plus 9, we've introduced an extra term plus 9, so we better remove it in order to maintain the equality. Similarly, we have y squared minus 8y, plus 8y. To write that as a square, we have y plus 4, quantity squared. Y squared plus 4y is 8y plus 16. We better remove that. And then finally, z squared minus 10z is going to complete as z minus 5 squared minus 25. Why the minus 25? Because this introduces an extra term of plus 25, which we have to get rid of. And then finally, we have another plus 25 that we didn't do anything with, equals 0. So this equation is perfectly equivalent to this equation after we've made these corrections and completed the square. These 25s cancel. This negative 16 and negative 9 sum to negative 25, which will move over to the right-hand side. And now we have it in standard form. Standard form is useful because it lets us pick off the center. Is 3, negative 4, 5. And the radius, if we notice that this is r squared, then r is equal to 5. This is a circle centered at 3, negative 4, 5 with radius 5. Let's look at problem 100. In problem 100, we want to find the vector with the given magnitude that satisfies the given condition. So we're given v, and we want to find a vector whose magnitude is 15 and points in the same direction as v. So probably the most direct way to do this is to first find a unit vector in the v direction. How do we do that? We need the magnitude of v, which is the square root of the sum of the squares. That's 4 plus 16 plus 1, which is the square root of 21. So the magnitude of the vector is the square root of 21. A unit vector in the direction of v would just be to divide by the square root of 21. And then if we want the unit vector, if we want to lengthen it so that it has length 15, we can kind of do this all in one step. We divide by the square root of 21 to make it a unit vector, and we multiply by 15 to then again stretch it out so that it has magnitude 15, and then we just take 2, 4, 1. So the vector that points in the same direction as v is this vector divided by the square root of 21. That makes it a unit vector, and then we multiply by 15. That makes its magnitude 15. In problem 107, we have a point that is equidistant from two other points that are given. Show that the point lies on the plane equation that looks like this. How are we going to do this? Well, we're going to take our generic point and we're going to compute the distance from that point to A and the distance from that point to B and set those distances equal to each other. So let me make a copy of this. It's going to be perfectly equivalent for us to compute the distance squared from here to here and the distance squared from here to here and set those equal to each other. And the advantage of working with distance squared instead of distance is we don't have the square root floating around. So let's compute the distance squared from P to A. Well, that is x minus 1 quantity squared plus y plus 1 quantity squared plus z minus 0 quantity squared. That's the distance squared from this generic point xyz to the point 1 minus 1, 0. Similarly, from P to B looks like this. X plus 1 quantity squared plus y minus 2 quantity squared plus z minus 1 quantity squared. That's the distance from P to B. What did we want to do? We wanted to set these things equal to each other, so let's do that. All right, we've got that. And let's simplify this as much as possible. I can tell just by looking at these squared terms that I'm going to have an x squared on the left and an x squared on the right, a y squared on the left and a y squared on the right, and a z squared on the left and a z squared on the right. They're all going to go away. So let's expand this out. There's the left-hand side. Expand out the right-hand side. Let me just check my work here. X squared minus 2x plus 1, y squared plus 2y plus 1, and z squared. X squared minus, plus 2x plus 1, y squared minus 4y plus 4, and finally z squared minus 2z plus 1. And as I suggested, these square terms are all going to go away. Like that. And we have a bunch of linear terms remaining, which we can add together and move to the left-hand side. So we have a negative 2x here and a 2x over here, so let's write that as negative 4x on the left-hand side. So we've got that taken care of. We have a 2y and a minus 4y. Move that over to the left-hand side, we get plus 6y. So we've taken care of that and that. We have a 2z over here, and there was no linear z term over here. And finally, we have the constant terms, which we can move over to the right-hand side. We have a 1 is 2, and we'll move that over to the right-hand side. And then also on the right-hand side, we have a 1, a 4, and a 1, so that's plus 6, 4. And then finally, we could simplify this a little bit because all of the coefficients are even. So we could write minus 2x plus 3y plus z equals 2, like that. And that pretty much matches the desired result, negative 2x plus 3y plus z equals 2. We haven't really explored more complicated plane equations like this one, but this does represent the equation of a plane. However, that plane is not parallel to any of the coordinate axes. It's a little bit more complicated. It's tilted and shifted around. We'll talk more about that a little bit later. Let's talk about problem 112. In problem 112, we have a force of 40 newtons that's acting on a box in the direction of the vector OP 102. Let's express this as a vector and then find the angle between the force and the positive direction of the x-axis. So let's grab a copy of that. All right, in part A, we're going to express the force as a vector using the standard unit normal vectors. So we want a vector that points in the same direction as P and has magnitude 40. To find a vector, so we need to find the unit vector that points in this direction. So the unit vector, in fact, let's use capital F since that's what we're given here. This vector is going to be 1, 0, 2. That's the original vector V. We'll divide by its length to make it a unit vector. What is its length? It's the square root of 1 squared plus 2 squared. And then we'll multiply by 40 to then scale that unit vector back out to the correct length. Find the angle between the force and the positive direction of the x-axis. Well, we have to think a little bit about this. We've got the vector here. It goes a little bit out along the positive x-axis and a little bit up. So it's a little bit out here and a little bit up like that. But it lies entirely in the xz plane. How do we know that? Because the y-coordinate is 0. So let's pull out the xz plane and just look at it on its own. And our vector here just goes out sort of like this, and we want this angle, the angle that it makes with the positive x-axis. Well, that is just going to be the arctangent of the opposite over the adjacent. What is the opposite side of this this little triangle here? What is this piece here? It's just 80 over root 5. And we're going to divide by the adjacent side. What is the adjacent side? It's 40 over root 5. So this is the opposite over the adjacent for this particular angle. We can simplify that. We flip and multiply. So this is the same as 80 over root 5 times root 5 over 40. And simplify to get 2. So theta is the arctan of 2. If we want to get a better understanding, a little bit more intuitive understanding of what the arctan of 2 looks like, we can just quickly jump over to Google and ask Google. So the arctan of 2 is 1.1 radians, and then we can convert those radians to degrees and see if it makes sense. I already forgot what the radians were. 1.1. All right, 1.1, 63 degrees. And does that look like a 63-degree angle? Sure. So about 63 degrees is the angle that the force makes with the positive direction of the x-axis. Let's finish up with problem 118. Problem 118, you have this sort of weird chandelier kind of thing going on. Make a copy of this. I find this problem a little bit less sort of intuitive. So you want to find the magnitude of the force of gravity acting on the chandelier if it weighs 5 kilograms. So gravity always acts down in this direction. That's the minus k direction if you're doing standard unit normal vectors. And there are these three sort of chains that are holding the thing up. And they're almost vertical, they're not quite vertical, and you're just asked to assume that the chains are essentially vertical. So what that means is these four chains are balancing out the force of gravity as it's pulling down on this 5 kilogram chandelier. If you look at the previous exercise, it tells you how to figure out the force due to gravity. If you know gravity is 9.8, then you just multiply by the mass to get the force, the magnitude of the force. So we'll take 9.8 up here. So for part A, 9.8 times 5 to get the magnitude of the force, and then it's acting in the downward direction. So the force as a vector is negative 9.8 times 5 times k. What's the magnitude of the forces of tension on each of these things? So the tension is acting in the upward direction, and the tension on each chain is equally distributed across the four chains. So the tension is going to be 9.8 times 5 divided by 4 times the standard normal vector in the z direction, which is k. They act in opposite directions, t going up, f going down. Okay, to wrap up, the suggested exercises, again, since we're doing all the objectives in this section, all of the exercises are kind of fair game. I meant to do this last time, but I want to talk a little bit about it this time. When you have a whole bunch of exercises like this, how are you to approach this? Are you supposed to do all of them? And honestly, the short answer is no. So then if I'm not supposed to do all of them, which ones am I supposed to do? What I want you to do when you're faced with a whole collection of these things is you notice that these things are kind of divided up into sections of problems. So here's one that's sort of all by itself. So you should understand that one. And here's one that's kind of all by itself. But here's a section of problems. Don't do all of these. Do enough of them to kind of understand what's happening and move on. Don't do all of these. Just do a couple. Maybe do one with a solution and one without a solution. And don't forget that the solutions are in the back of the text. So if I'm working on 67, I click on this hyperlink, it's going to drop me to the back of the book and show me problem 67, which is right here. Oops, problem 67. And then if I want to go back, I can just click this link and it'll send me back to where I was. Again, here's another section of exercises, another section. So if you feel like you're not getting it, yeah, you might end up doing all of these exercises. But if you do feel like you're getting the idea in a particular section, don't do them all. Maybe look at them all and say, hey, I think I could do this, this, and this to get me to where I want to be. Once you've sort of convinced yourself or you feel comfortable that you have all of the objectives, then jump over to web work and do the assessment for Chapter 2, Section 2. Thanks.